So I will two things. So first of all, I think it's it's good if we have one moment at some point during the conference. I think this sort of middle point, end of the first 2 weeks, is a good moment to mention Oded. First of all, I guess most of you who've been following sort of the first, all the courses of these first 2 weeks will recognize or will have recognized how much everything that has been taught in these first 2 weeks is really, I mean, due or very much due to what Oded's mathematics, and you've seen many of his theorems proved, and we should say that sort of in 2007, when we started thinking about organizing this school, that was this Park City meeting, and one of the key things for us was, to make sure that Oded would be there. And so he was planning to come, actually, which is, he was not a keen traveler, so but he said, okay, now this I want to come, and so of course it's very sad that sort of he passed away sort of now 2 years ago already. And so for those of you, I mean, I don't want to make another memorial session type thing, but I think it's important for those of you the younger people especially, who did not know Oded, just that to mention that in addition to all his great mathematics, he was just also a great person, and that we all miss him very much, and that definitely this summer school here would not exist, without his mathematics, and also his general attitude towards people and mathematics, because the way he was sharing things, and many of us who you are hearing have been co-authors of his, and we teach what we learn. We teach you what we learn from him also, and that's sort of a way to spread also the different mathematics that he started. Is also one of the main goals of this school. And I don't want to say much more, but if you like his mathematics, or even if you don't like it, then I'm sure you will have liked the guy, and it would have been great to have him around during the weekend, enjoying surfing or whatever activities. Okay. So maybe now I just want to say a couple of words about how we organize the coming 2 weeks, because after Jeff's lecture, it's sort of halfway through the school, and as you will have noticed in the way we try to set up things, this first part we had these 3 foundational courses that were lasting 2 weeks, and now we turn to sort of a cycle where you will have sort of courses that last 1 week each, which are called these mini courses. Basically, each course will consist of 5 90-minute lectures, and sort of next week the 3 lecturers will be Greg Lawler, who will talk on sort of further questions related to SLE, Hausdorff dimensions, and parameterization of the SLE curves. Whether it's it's a random fractal. What can you say about it? You will have Scott Sheffield, who will focus on the relation between SLE and what is called quantum geometry, try to view an SLE curve as a way to glue together 2 complex structures. And Stas Smirnov, who is going to focus more on the discrete Ising model, starting with the discrete Ising model, and show how to get conformal invariance and on various aspects of the relation between the Ising model and SLE and other things. And maybe you have not, it was maybe not completely apparent during these first two weeks, but the 3 courses, the themes of the 3 courses you had during the first 2 weeks are very much, interrelated. And we hope that the relation between the different courses will become more apparent with these more advanced courses. So in addition to that, there will be more seminar evening type talks, which will be more of a research type. So we will ask the people who present something to keep in mind that it's not really like a talk in a research conference. It should still be sort of user-friendly, not to try to not to go too fast. So that's one thing. The other thing is that it is important that you tell us, to the organizers, you know, if you have the feeling that some course is going too fast or something is not, that you are not able to follow everything that is going on, then you know, and if you don't dare ask directly to the speakers, which is something we encourage you to do anyway, but then you can tell us, and then we will try to convey the message that they have to slow down or, you know, adapt more to the audience, right? I mean, the course is not for speaker. I mean, the school is not for speakers to have fun on the stage. It's for you to have material to work on. So you should really tell us. So since there were complaints about the fact that you know, the weekend is shortened by Saturday morning. So maybe I describe to you just very briefly what will happen on Monday, so that those of you who want to skip Monday morning can do it. So basically what is, just practically what is happening is that some of our main speakers of next week will arrive either late on Sunday or some during Monday. So basically they will not be ready to lecture on Monday morning. So the question was what the, you know, best thing to do on Monday morning. So we decided that we would use the Monday morning to do some to present some basic preparatory material that might help you following these courses. So in the first slot on Monday morning, from 9 to 10:30, I will try to give basic material on what Hausdorff dimensions are, going slowly through, you know, what is Frostman's lemma, why do we need second moment estimates and things like that, so that you have a clear picture of some of the things that will go on in Lawler's lecture. And I'm discussing with them to know what would be most useful for you to really know. So if you know all this already, don't need to, you can, you know, show up later. And then in the second slot, I think I will do something similar for Sheffield's lecture. So I will try to explain slowly various ways to intuitively and formally understand what the Gaussian free field is, why the Gaussian free field is related to SLE4, and slowly trying to get you some feeling about it. Also, maybe some more things about Green's functions, since Greg will try to explain to you what a Green's function for SLE might be, or things like that. So so basically Monday morning will be sort of really background material. You should not consider it as sort of advanced material. If you are already, you know, advanced researcher in the field, you might just skip this Monday morning. And in the afternoon, there will be two seminars, one by Yves Lejean, one by Remco van der Hofstadt, and the first course by Greg will start on Monday afternoon. And then we'll continue. So each of the 5 courses will have, in addition to these initial background sessions, there will be one, at least one tutorial session, maybe more. We'll see, depending on how things go. Okay, so again, so just to conclude and with the dead, I think at some point it's nice if at one nice moment when you dive into the nice water this during the weekend, the sea and so on, and you have a thought of this nice guy. It's a good way to remember him, because I'm sure he would have loved, you know, being with us and having a nice time here in Brazil. Okay, so now it's leave the stage for Jeff's last lecture.
So before I start, also since this is halfway through the course and a number of the speakers are leaving today, I think it's a good opportunity to thank the organizers, Vladas, Vendelin, Chuck, and David for organizing this, and especially for Vladas for handling the local situation here. So I think they deserve a round of applause. And another comment I want to make before starting the lecture, referring to Oded, was since this was sort of more of a course rather than a seminar, it wasn't always mentioned what he did, but just to exactly as Vendelin said, as far as the noise sensitivity, in all that you've learned 3 different techniques for the spectrum: the hypercontractivity, the randomized algorithms, and the geometric spectrum. And he was a central role in all 3 of these different approaches. So that's also clear from the notes, but just to clarify that. Okay. Before starting on the last lecture, which is dynamical percolation, maybe since there's a number of French people here, let me tell you how dynamical percolation sort of arose. So in 1995 at the Mittag-Leffler Institute, I was giving a talk on percolation on joint work with Ronald Meister. And at the end of the talk, Paul Maliavan asked a question. And I didn't understand the question, so I figured the next day I would go into his office at Mittag-Leffler and ask him what he meant. So we spoke for a while. I left, and I still didn't quite know what he meant. So then I spoke to Ulla Heckstrom, discussing what he might have meant, and then sort of this version of dynamical percolation arose. I don't know if that's what he meant or not to this day, but he might have, and that's sort of how some of it started. Turned out we found out a few years later that Itai had also come up with the model earlier, the idea of the model, but didn't pursue it. Okay, so that's the history. And also let me mention that one of the things you'll see how to do today, it was in fact, as far as I understand, one of the motivations for this noise sensitivity paper by Benjamini, Kalai, and Shrum that was discussed at the beginning. It was to solve, one of the motivations was to work on a problem in dynamical percolation, which I'll explain to you. Okay. So today's lecture is on dynamical percolation. For those who were at the exercise session yesterday by Ragnar, he introduced the model and proved some elementary properties. Of course, that's not a prerequisite for this lecture. So mainly, we're going to move very quickly to the d-dimensional lattice and then to the 2-dimensional lattice, because that's where the most interesting things are going on. But for the model, I'll introduce it to you in a more general context just to warm up. So in the general context, we have an arbitrary infinite graph with vertices v and e, and we have some parameter in 0, 1, which is usually going to be our percolation parameter. But what we want to do is, so far in this course, we've just studied percolation. Not just, but we've looked at percolation and discussed it quite a lot. And now what we want to do is to introduce a time dynamic. So we want to have the percolation evolving in time in some way. And we want to have it evolve in the absolutely simplest possible way you could imagine. And the simplest possible you could imagine is, well, if I look at each edge, it's either in 2 states, 0, 1, 1 is on, 0 is off, and I could just have it evolve in time according to a 2-state continuous time Markov chain. And I do this sort of independently all over, and this is what dynamical percolation is. So here is how it works. Each edge independently behaves as a two-state Markov chain with rates. This is where my parameter comes in. So what this means is we say 0 goes to 1 at rate p. In other words, what this means is you wait an at rate p says you wait an exponential amount of time. You wait an exponential time with parameter p and then change to 1. And similarly, if I'm in state 1, I wait an exponential amount of time with parameter 1 minus p, and I switch to 0. Okay, simplest two-state Markov chain. And now each of the edges independently does this. So if we let pi p be the ordinary product measure, this is the usual, when we do independent percolation on each edge present with probability p and off with probability 1 minus p, of course, this is the measure we're using. And now this measure is stationary, is trivially stationary for the dynamics. In other words, if you start with ordinary percolation with parameter p, I run my dynamics, I look what happens at time 13. What do I see? I see an ordinary percolation realization. The measure at time 13 is also product measure with density p, because I started with the stationary distribution, and this trivial dynamics preserves that. So we have, I guess we could say, distribution at all times is pi p. Okay? We can do this for any parameter p. Very soon we'll move to the critical parameter where it's interesting. But let me tell you what the question is. Do there exist times t where the percolation picture looks different? So could it possibly happen? Could there be some random times t, suddenly you see something you would not expect to see? So a particular, this is of course a vague question, a particular question we could ask is, so this question turns out to be extremely easy, but the point of the question is to get you thinking in the right way. Let's take a value which is less than critical, and I could ask, if I look at the probability there exists some time t such that at time t there exists an infinite cluster, is this bigger than 0 or equal to 0? So of course, since we're below criticality, if you look at any fixed time like time 102 and see what you have there, of course you see ordinary percolation. So with probability 0, you'll see an infinite cluster. Now the question is, can with probability 1, you won't see an infinite cluster. Now you can ask, well, okay, but if there's a lot of possible times, is there maybe some time at which an infinite cluster appears? If time was discrete, if we were doing this in discrete time, the answer would be completely trivially no, just by countable additivity. If it doesn't percolate at a fixed time, when I say percolate, I mean there exists an infinite cluster. That's what that expression means. So if there are countably many times, of course, by countable additivity, there could never be a time at which you percolate. But here we have an uncountable number of times. So you could ask the question, and this is the type of question we want to ask. Turns out for the subcritical case, it's an easy question, but this question is to get you in the right mood, right mindset. So let me just make the first statement. The proposition is basically no, or well, that wasn't a yes/no question. So it's equal to 0. That's the proposition, and it's an elementary exercise. It was done in the exercise session yesterday. If you watch this thing, you'll never see a time at which percolation appears. So I'm not going to I won't prove that. We won't need it for things later, but it's very elementary. But this sort of more or less tells us right away we're going to stick to P equals PC, the critical value. You might wonder what happens above PC. What happens is exactly what you'd expect happens, namely above PC. If you look at a fixed time, there'll be an infinite cluster somewhere. And it's also the case that at all times there'll be an infinite cluster. You won't have an exceptional time where you don't see an infinite cluster. So everything behaves very simply away from criticality, so we stick immediately to criticality. The first result, which I won't prove because I want to move pretty quickly into the d-dimensional lattice and then the two-dimensional lattice. So this proposition simply says that dynamical percolation is potentially interesting, that you can get this phenomenon where even though ordinarily you don't percolate, there are going to be these strange times at which you do percolate. So there does exist some graph G such that theta, we've only defined theta on the ordinary on ZD, but you can define it on any graph. So theta of PC is 0. So that just means you don't percolate at the criticality. At criticality, this is what we expect of most reasonable graphs. There are graphs where this is not true, but it's believed to hold for all transitive graphs. There exists a G such for that. But if you run dynamical percolation at the critical value, which I'll put down here, probably there exists a T such that we percolate at time t is equal to 1. So if you run this thing in time, suddenly there'll be these strange times which appear where you get a cluster. Okay. And a quick comment, Fubini's theorem, if you sort of apply Fubini's theorem to probability space cross time, it's pretty easy to show that if you look at the set of times at which we percolate at time t, this is going to be, the point is we can make the set non-empty, and it will happen very rarely. And what's going to happen is if you look at the Lebesgue, dx stands for Lebesgue measure, if I look at the Lebesgue measure of these times, this will be 0, almost surely. So almost surely this time will necessarily have Lebesgue measure 0. Once something has Lebesgue measure 0, if it's still there, it's natural to ask how big it is. Now you might say, oh, it's not very big, it has Lebesgue measure 0, but that just means you're not using the right microscope. Once something has measure 0, you should start looking at things like Hausdorff dimension, which will be explained to you on Monday. And for certain situations, you can even, in certain of these graphs, you can figure out what the Hausdorff dimension of this time is. So this was done much earlier. And you can do a lot of this stuff on a lot of things have been done on trees, and you can compute Hausdorff dimensions. Okay, that's a couple first results about percolation, about dynamical percolation. Once you know there's such an a graph like this, the original constructions are sort of strange and not natural, so it'd be immediately natural to say, okay, I don't care about weird graphs. I just want what happens on the graphs we know and love, the d-dimensional lattice. So would one expect if we run, so you should recall that, I don't remember what facts of the following you've learned that were presented here, but if you take the d-dimensional lattice, at the critical point, we know, of course, you don't percolate in 2 dimensions, and you also don't percolate in higher dimensions, 19 in higher dimensions. And it's an open question whether you percolate in 3 dimensions. So let's stick to those cases, the 2-dimensional case and the high-dimensional case, and ask the question, even though the question is, okay, in those cases, the 2-dimensional case and the 19 and higher dimensional case, theta of PC is 0. So if we look at a fixed time, there'll be no infinite cluster. But if we run this in time, will an infinite cluster appear? That's the question. And we ask this in 2 and 19 dimensions. Okay, so So this result says that on the high-dimensional case, in the high-dimensional case, there are no exceptional times. If you watch this forever, you'll never see an infinite cluster appearing. So I sort of want to give you the outline of this proof. So it's quite simple using a highly non-trivial fact. So there's two. Well, first of all, so the fact that theta of p is 0, this is due to Hara and Slade. But there's something special in 19 and higher dimensions which does not occur in 2 dimensions, which is the following. If we look at the percolation function and we draw it, turns out you can draw a linear line right above it in high dimensions. So theta of p is less than or equal to some constant times p minus pc. This inequality simply tells us it's bounded above by a linear function. Loosely speaking, the derivative at pc is finite. This stronger fact is due, I won't go into the details, but sort of Hara, Slade, and Barsky and Eisenman. Oh. Okay, so let me argue, based on this, why there's no exceptional times. And basically, the proof of this is going to work. The proof of this works with any graph which has this property, that the derivative of the percolation function at the critical value is 0. Okay. So I'll simply show you the probability that there exists a time t in 0, 1. I can restrict to the unit interval by countable additivity. And I also can restrict to asking whether the origin percolates, because there's only countably many vertices. This, of course, 0 is connected to infinity time t. So I want to show this is 0. So this is a unit interval, and I'm going to break this up into intervals of size 1 over m. So here's 0, here's 1 over m, here's 2 over m, etc. And I'm going to let ek be the set of edges E such that E is open sometime in the kth interval, which we'll take to be from k over m to k plus 1 over m. So I consider the set, I look over here at the kth interval, k over m, k plus 1 over m. I just look at this small time unit, and I look at the set of edges which are open sometime during that interval. So first of all, since the dynamics are independent from edge to edge, certainly which edges belong to EK are independent of each other. So this EK is simply a random set of edges, each one independently. But what is the probability that an edge belongs to? What is the probability that a given fixed edge belongs to the set? What's the probability an edge is open sometime during here? Well, there's two possibilities. One is it's open at the beginning of time. The probability that it's open at the beginning of time is exactly p. Or it could be off, and then it could switch on during a time interval, a time length of 1 over m. It's easy to see that's basically 1 over m, maybe 2 over m, a constant over m, but more or less 1 over m. So this is the probability that an edge is in EK, exactly p plus 1 over m. And so now if I look at the following, so what this means, what this means is I want to know, is there a path from the origin out to infinity consisting of edges which belong to ek, consisting of edges which are open sometime during the kth interval? Well, this is simply an ordinary percolation realization. Every edge is in there independently with this probability. So this is nothing but theta of p plus 1 over m. But now the percolation function has a finite derivative at the critical value. We have this inequality right here. And so this is at most constant, basically 1 over m. So if I look at any particular interval, the probability there's a path from 0 to infinity is at most order 1 over m. And now I let nm be the number of intervals where this occurs. So I look at the set of all k's where, if I look at the edges which are open during that interval, I look at all those k's and I simply take their number. The number of intervals where this occurs. Now there's complicated dependencies. Whether this occurs for one k and another k are highly dependent, but I don't care. I want to compute the expected value of nm, and there I can use linearity, and I get the expected value of nm is at most, well, how many possible k's are we looking at? M of them. And for each of those k's, this is occurring with this probability. So this is a constant. Then, if we what we're really interested is in the set where we percolate. If we look at the set of times at which we percolate during 0, 1, so I look at the cardinality of this set, not the Lebesgue measure. I actually look at all the times during 0, 1 at which the origin percolates out to infinity, and I count the number of those. And it's not so hard to see that n is at most the lim inf of the n sub m's. Okay, why is that? Let's say n were 7. Let's say there were 7 different points. Well, let's say 4 to save myself time. So there were 4 different points at which we percolate. Once m is large, these intervals I'm looking about, these small intervals, will be all disjoint. And now, since at this time I percolate, I certainly will percolate if I look at this interval of time and look at the edges which are open sometime during there. I'll certainly percolate there too, and similarly in those other 3 intervals. So it's not so hard to see. We get this inequality. Now we can use Fatou's lemma, and we conclude the expected value of n is at most the expected value of this lim inf, but that's at most the lim inf of the expected values. So by Fatou, this is at most lim inf over m of the expected value of nm, and those are all at most a constant. So we end up getting this is most a constant. So what this shows is if we look at the set of times at which we percolate during the interval, the expected number of times is actually finite. That, of course, tells us only a finite number of times. So now we know there's only a finite number of times at which we percolate. You might believe that from that you can conclude there's none, and in fact you can conclude it. I'm not going to do it for you, but the picture might be in mind. It's sort of like a Brownian. If you have a Brownian motion, a Brownian motion cannot have an isolated 0. Brownian motion sort of can't hit 0 and pop up. All the zeros are sort of it's a so-called perfect set. There's always other zeros nearby, and you can't have these isolated things. And you can show for this model too, you can't have isolated points where you percolate. So once you have a finite number, you end up having none. I'm not going to outline that for you. There's actually 2 approaches. One is a hands-on approach. That was the original approach. There's also, in fact, some very horrible general Markov process theory, which you definitely don't want to see, that also allows you to make that last step. But at this point, you can just take my word. So this was a complete proof. There's only finitely many. And from that, you can get there's none. OK. So let's move on to, so that solves the high-dimensional case. What about the two-dimensional case? Well, this thing here, this was proven in high dimensions, but in 2 dimensions, it's actually false. So this is false. In 2 dimensions. You don't have a derivative. You have an infinite derivative. In fact, maybe in the course, I don't remember, in the SLE course, you were told sort of what the derivative is. It behaves like a power. If you go epsilon on out, you can say what the power looks like. But anyway, it has an infinite derivative. This method of proof completely fails. And so before answering the dynamical percolation question, let me tell you a result from the original BKS paper, the noise sensitivity paper, where they concluded something maybe like this using the noise sensitivity. So, run dynamical percolation on a square on an n by n square at criticality. I won't even say that because we're completely doing things at criticality. And I let Sn be the number of times we change from our function being 1 to it being 0. What do I mean by that? Our function is exactly the function that we have a left to right crossing. If there's a left to right crossing, it's 1. There's no left to right crossing, it's 0. So basically, I am looking at this picture, and I'm just looking all the time whether there's a left to right crossing, and I count how many times during this interval when it changed from yes, there's a crossing to no, there's no crossing. And their theorem is that Sn is very large. If n is very large and you run this thing, you'll see it going back and forth, off on, extremely many times. And the exact statement is that Sn is approaching infinity in probability. Okay, they're, of course, defined in different spaces, so this is all the right type of statement you would want to say. So, and this is just for unit time. It's very important. If I ran infinite time, this is not an interesting thing. So number of times in the unit interval. So it goes back and forth very quickly. Maybe this will start to suggest in 2 dimensions things are happening so quickly, maybe there'll be an exceptional time. I mean, somehow, to get an exceptional time in 2-dimensional percolation, you want the whole picture to change very, very, very fast and rapidly, and maybe you'll get lucky and you'll get an exceptional time. And that starts to sound like things from noise sensitivity. So we want to now go to the 2-dimensional case. Let me first quickly put so at this point, we're going to restrict to the 2-dimensional lattice or the triangular lattice, the two of them. And so since the critical value is 1/2, we have this picture. But let me define these dynamics slightly differently. To switch your state at rate 1/2 is identical to re-randomizing with rate 1. So this is the same as re-randomize at rate 1. That means each edge or hexagon weights an exponential manner with parameter 1. When the clock goes off, it throws out its old value and then takes a new one, black or white, each with probability 1/2. Things are starting to look a little bit like noise sensitivity. So what I want to explain today is how you can prove things about exceptional times, what you can prove, and I'm going to do them with both methods, the randomized algorithm approach and the geometric approach. And the geometric approach gives stronger results, just as it did in the noise sensitivity. So I'm going to start off by telling you what the randomized algorithm approach does. So what does the randomized algorithm method give? So although I'll repeat it, let me tell you in advance what the different things gives. So this method will allow us to prove there are exceptional times of percolation on the triangular lattice. And it will give a certain bound on the Hausdorff dimension of the times. What it could not give is it couldn't give the exact Hausdorff dimension of the times, and it didn't prove the existence of exceptional times on the two-dimensional lattice. And for those, to get the exact Hausdorff dimension on the triangle lattice and to get exceptional times on Z2, then we need the geometric approach of the spectrum. And it's not, and the reason, of course, we can do more on the triangle lattice on Z2 is because, as has come up many times in Vincent's course, we know a lot of the so-called critical exponents in the critical exponents for the triangle lattice, and these are believed but not known in the two-dimensional lattice. Okay, so theorem for the triangular lattice, there exists T such that the origin is, say, the center hexagon. So I run this at criticality. Well, let me say positive, and then just there exists T in the unit. Oh, I have the T in the wrong place. The probability that there exists a T in the unit interval of time such that the origin percolates out to infinity at time t is positive. So in particular, once this is positive, you'll immediately, by thousands of different 0-1 laws, know there'll be exceptional times of percolation. So we get these on the triangular lattice, and I basically want to explain get a more or less complete outline of the proof of this. Okay, so it's going to be the second moment method. You've seen one version of the second moment method in the exercise session yesterday, which is, of course, not allowed to be a prerequisite. So what I'm going to do is define xn to be the following random variable. If I ever write an n at some point, please yell at me and tell me to turn it into an r. My notes seem to have r's and n's, and they're supposed to be the same thing. So this is the R ball. Often, in ordinary percolation, we often look at the probability that there's a path from the origin out to the boundary of the R box. Before, let me just recall the probability. This is for ordinary percolation, that there's a path from the origin out to the boundary. dr is the ball of radius r. The boundary means the outside. This probability, which we call alpha 1 of r, this is more or less 1 over r to the 5/48. There's little o of 1s in the exponent as usual, but we don't worry about that. Okay, so this you recall, and this is my random variable. I integrate from, this is a random variable, I integrate from 0 to 1 of the indicator function that there's a path from the origin to distance r away. I integrate that over dt. What's another way of describing this? Xn equals the Lebesgue Lebesgue amount of time in 0, 1 for which the origin is connected to distance n away. Computing that integral is simply adding up the amount of time where this event occurs. So you're just looking at the Lebesgue measure. What is the expected value of xn? xr, did I already? Well, if I fix the time I'm looking at, the probability that the origin connects to r away, this is what we call alpha 1 of r. And we're just integrating this for 1 unit of time, so you can easily use Fubini's theorem, pull in the expected value, and through the integral, and this just becomes alpha 1 of r. The key step, and which is called the second moment method, which is probably going to come up in the background course on Monday morning, perhaps, in Greg's course, is the following thing. There exists a constant c, positive, such that the expected value of xr squared is at most a constant times the expected value of xr squared. I said them the same, but there's an important difference, for all r. So there's a universal constant so that the second moment, for all the r's, the second moment is at most this constant times the first moment squared. Okay, this is where the work is. Using inequalities like this is what is called the second moment method. So let me quickly finish the proof of this, assuming we have this key step. And then the work we'll be doing in the key step. So assuming the key step, we have so this inequality is nothing but the Cauchy-Schwarz inequality. Easiest way to see that, you bring this to the other side, and you write the random variable xr as xr times the indicator function that xr is positive. So this is the same as xr times the indicator function xr is positive. That's the same random variable. And then you apply the Cauchy-Schwarz inequality to that product, and this thing pops out. Okay. Now, if we assume this thing here, the key step, that tells us that this denominator doesn't get so much bigger than the numerator. And in particular, by the key step, this is bigger than or equal to 1 over r constant. And this is true for every r. These events, that xr is positive, these are decreasing sequence of events as r goes down. If there's a positive amount of time at which you're connected to 100 away, then there's certainly a positive amount of time you're connected to 99 away. And so these are a decreasing, and so by countable additivity, I can say then the probability of their intersection is bigger than this. So by additivity, we get this. And this sort of, and now I want to claim this event basically tells you there's an exceptional time. This event says, okay, for every r, there are times at which I get r away. Then there are other times I would get to r plus 1 away. And then r plus 2 away. So you could try to intersect these sets and get something. Now, there's a tiny technicality I'm absolutely not going into. It's very easy. The set of times at which this is positive is not a compact set. So you can't just take an intersection of non-empty compact sets and say the intersection is non-empty. That doesn't quite work. But an easy fix does that. So, okay. So that completes the proof subject to the key lemma. Okay, so we need to compute. This is all we want to do. So what is the expected value of xr squared? So xr is sitting over here. What happens when I multiply that? It's basically just like when you square a sum. So when I square this, I write this as one integral. I write this as this integral times the integral again, this time with the parameter s. And then I multiply them out, and I get a double integral. So let me do this let me show you what you get. So if I didn't have the probability there, if instead remove the probability and take the intersection of this event means I have a t and an s here. This means that there's a path from the origin to r away, both at the times t and at the time s. If I simply had the indicator function of that instead with the double integral, that would be exactly my xr squared. When I then take the expected value, I push the expected value through the double integral, and I simply get exactly this. Now, this thing, the probability that you have a path from 0 to r away at times t and s, it's clear this only depends on the distance between t and s by stationarity. And so I won't write it by stationarity. It's very easy to check. Basically, this is at most a single integral. And I look at the probability that I am distance r away both at time 0 and at time t. Okay, so now notice if maybe I write this instead like this, two events. That's r time t. So I want both of these to occur. Now notice how if these events were independent, I could write the probability that both occur as the probability of this times the probability of that. Then I could factor things out trivially and get this becomes more or less the expected value of xr quantity squared and be a complete triviality. Of course, the point is these are not independent, and when t is extremely small, they're highly correlated. If you imagine t enormously small, much smaller than r, of course, these are more or less the same events. In a small amount of time, nothing's going to happen. So the problem is this probability is much closer to just the probability of the first one when t is small. And basically, the goal is to figure out how to estimate this correlation. OK. So if I let omega 0 be the configuration at time 0 and omega t the one at time t, notice that in distribution, this is the same if I look at simply 2 times time 0 and time t, omega t is simply a noise version of omega 0. It's exactly what we did in the noise sensitivity part of the course. Because if you look at one edge at time 0 and time t, there's a certain probability it's going to be re-randomized, and a certain probability it won't be re-randomized. Now, if I look at my fixed edge, what's the probability that it's re-randomized before time t? Well, it gets re-randomized at rate 1, an exponential with rate 1. The probability gets re-randomized before time t is 1 minus e to the minus t. So if this is the time you're looking about, you're re-randomizing with a probability 1 minus e to the minus t. This notation here is referring to the noise sensitivity part of the course. This is your IID sequence, and this is your epsilon noise. So this thing is exactly our noise version. And notice that the interesting things occur when the noise is small. The problem we have is when t is small. That's where the correlations are getting big. And so fortunately, everything's working out. When t is very small, this whole thing is very, very small. And so small t questions get us back into small t questions for noise sensitivity. Okay, so this integral, just to put this into the context, this is not exactly how I want to approach it, but let me write this integral, this probability in terms of Fourier coefficient, just so we see exactly this is corresponding exactly to our noise sensitivity thing. So this thing here, let me write it out and then convince you. Now I only need, these are really functions of just a finite number of random variables, because to know if this occurs, you only need to look at the ball of size r. So we really have a Boolean function. And the edges are on and off with probably a half. So we're exactly in the setup of a finite Boolean function. And this is our formula for correlation like that. So it comes down to this. So remember what went here in the noise sensitivity expression. It was 1 minus epsilon raised to the s. If this is our epsilon, 1 minus this is simply you're left with the e to the minus t term. And so then I have the e to the minus t term raised up to the cardinality of s. So just that basic noise, or basic way of writing noise sensitivity for coefficients is exactly this. This thing here I should have written more clearer. What is the function f here? I call this fr. Fr is simply the indicator function that we have a path from the origin to r away. So Fr is simply the indicator function that there's a path from the origin to distance r away. Okay. So our Boolean function fr, there's no time here now. We've represented our time question back in terms of this basic function. So when I write fr as this is simply the ordinary Boolean function. You're looking at things at a fixed time that there's a path from the origin to r away that I call fr. And our noise sensitivity tells us exactly this. So now we have now we know what that correlation looks like. What we need to do is I need to play with this and try to say something intelligent about it. So at this stage, I'm sort of doing both proofs, both the randomized algorithm proof and the geometric proof. I have it. This is all completely general. Now continuing with the triangular lattice, what I want to do is to be able to understand these Fourier coefficients via the randomized algorithm. Okay, but okay, might be what I want to do, but in fact, I'm going to use a slightly different. For the randomized algorithm, you have to use a slightly different approach. So the geometric proof, we would start analyzing the Fourier picture of these functions. For the randomized algorithm approach, we have to make a different change, do something a little differently, and analyze the Fourier behavior of a different picture. So going back to this thing, so this will be try to keep this in mind for the other argument. So for this one here, if we go right here, what I want to do is the following. Have a picture here. This is little r, and this is some much bigger r. What I'm going to do is I want to break things up into two scales. So this probability over here, this is at most the So if there's a path from the origin to big R way, both at time 0 and time R way, two things have to occur. At time 0, there has to be a path from 0 to little r way. And then in the annulus from little r to big R, there has to be a path both from the origin and time t. This doesn't guarantee that, but this is an upper bound. Now you might say, okay, but there also has to be a path at time little t, at time t from 0 to little r. I say, yeah, but I'm going to throw away that term. You could imagine if r is fairly small, I'm not sort of giving up much. The things are so correlated during this small amount, in this region, I'm perhaps not throwing away so much. But as far as the proof, I don't care what I'm throwing away. This is going to be the bound I want to look at. This thing here is nothing but our alpha 1 of r. And so what I want to do with the randomized algorithm approach is I want to get a bound on this. I want to get a bound on the probability that there's a path in the annulus from little r to big R, both at time 0 and time t. And I'm going to try to do this by our noise sensitivity thing. So this event, let me call this f sub r big R. This is the indicator function that I have this path in the desired annulus. So this is R, this is big R, and I look, is there an open path from, open will always be white, from the little r box to the big R box. That's my function f r r, I'll call it. And to obtain this correlation, to understand this, I want to look at the Fourier picture for fr. So I'm going to ignore this term for a minute. I come back to it later, and I want to look at this picture. I want to look at that correlation, and this is going to be this let me rewrite it here. So from r to r, both at time 0 and time t, I can write that as the expected value of FRR squared, that's sort of f hat of the empty set squared, plus the sum k equals 1 to infinity. I sum up the Fourier coefficients of size k, FRR hat squared of s, e to the minus tk. That's basically what we had. That's similar to what I had here, but now we're going to look at this function instead. OK, so I want to get a reasonable bound on this. And the way I'm going to get a bound on this guy is by using the revealment theorem. So I'm going to bound this by the revealment theorem. So I want to find a reasonable algorithm to detect if there's a path from the little r box to the big R box. Well, this is sort of similar to when we were finding algorithms for crossing probabilities. It's a little different. The thing you want to use is, rather than sort of a chordal interface, you want to use more of a radial interface. And so I'll just call that the proposition, and we'll do that, look at it after. There exists an algorithm A for the event, this event, where the revealment of this algorithm is at most alpha 2 of r. Remember, alpha 2 stands for the 2-arm exponent. Alpha 2 of r, alpha, then alpha 1 of little r to big R. Okay. Let's assume that for the moment and then fill things in and see what happens. So this term is well, what we call alpha 1 of r squared. This is simply the 1-arm multi-scale event from little r to big R. I sum k equals 1 to infinity. Now I use the revealment theorem on this term using this. Now remember, the revealment theorem said a term like this is at most the revealment times k times the L2 norm of the function. When we're doing crossing events, we threw away the L2 norm of the function. We said, well, that's about 1. We don't care about that. But here, this probability is extremely small, and we don't want to throw away that L2 term now from the revealment theorem. So what we get here is we get, there's O of 1s all over the place. I'm not going to worry about that. So this will be alpha 2 of R, alpha 1 of R, big R. Okay, that's the revealment times K times the L2 norm of the function we're looking at. That gives me another alpha 1 of R, R. And then I have my e to the minus tk. OK, so what happens is, let me just, it's probably easier if I write down a line and then convince you it's true. OK. I pulled this alpha 1 of R, R squared. I have 2 copies of that, 1 here and 1 here. They get pulled out of both the sums. This one I have 1. What's left is alpha 2 of R. That comes out of the sum. And then I'm simply left with this series, k e to the minus tk. This term here, it's not hard to show that this is at most c over t squared. The easiest way to see that without doing the mathematics is you can sort of think of this as the mean of a geometric random variable with the parameter t. You have to throw in 1 extra copy of t to really have the distribution of the geometric, and then the mean is 1 over t. Anyway, it's elementary to check you get that. OK? So this is where we have now. This didn't. We forgot about this term here. Let me add that back in. So I want to get the alpha 1 R back in. So what I end up getting I won't worry about constants. OK, so what's happening when I multiply a term? What I'm using is the quasi-multiplicativity. Something like this and something like this is about the same as going all the way from 1 to R. This is our quasi-multiplicativity that has come up. When I multiply that alpha 1 of R by one of these, I get this one. And then if I took another one and multiplied it, I would get that, and I compensate with this. So maybe that was a little quick, but it's easy to check that this is the type of thing you end up getting. OK. Now, so this is where I am at this point. Where we want to go. What do I want to do? This term here, alpha 1 of R, this is exactly the expected value of xr sitting right here. It's squared. That becomes exactly the expected value of xr on the right-hand side. I'm left with this term, this and this. What I need to show is that somehow this is still the integrand. I want to show when I integrate this over t, I get a finite number. So I'm going to have to do So let me just recap where we are. So Long walk back and forth. Okay, I think we have that. Okay, this is at most alpha 1 squared over alpha 1r, 1 plus alpha 2 of r over t squared. Okay, now I have my little r available. I haven't told you how to choose r. That was sort of this intermediate scale that I want to use. Now, it'd be natural to make that, it's much smaller than big R, but it might get very big when t is very small. So the idea is I want to make, this thing is order of 1, so I should choose R, so this is of order 1. Choose R such that alpha 2 of R over t squared is of order 1. What should I then choose R to be? Well, you have to remember the 2-arm exponent of R. That came up in the ordinary revealment, what that exponent was. And this is nothing but 1 over R to the 1/4 power. Forgetting O of 1 terms, alpha 2 of R is this, times 1 over t squared. So I want this to be of order 1. So how should I choose R? I should choose R, which is allowed to depend upon t, to be t to the 8th power. If I choose R to be t to the 8th power, 1 over t, t to the minus 8th power would be better, then this thing will be of order 1. So that's my choice of R to the t. When I choose R of t to be t minus 8, this term just becomes a constant. This is of order 1, so this becomes a constant. What happens with the term over here? Yep, I haven't, yep, I still have to integrate. I'm almost done with the integrand. Okay, so, yeah, this is, I'm sorry, right. Okay, yeah, now I see your point. This was supposed to be the integrand, so good point. I'll do the integration now, thanks. Okay, so this term has disappeared. What does alpha 1 of R of t become? So this whole thing becomes, I get the alpha 1 of R squared comes out, and I'm left with 0 to 1 dt of, this is of order 1. I get 1 over alpha 1 of R. So this is 1 over alpha 1 of R of t, which is t to the minus 8 dt. Now you use the arm exponent alpha 1. The 1-arm exponent is 5/48, so this thing ends up becoming 0, 1, t to the minus 8 times 5 over 48. Now you have to check a million times. There's all these 1 overs. Here's a 1 over. It's 1 over this, and alpha 1 is 1 over. But in the end, you check. You end up getting this. I have my mean here, xr squared. So you have to make sure this is integrable. That's the same, of course, as t to the minus 5/6 dt. And you're done. So since this is integrable, because fortunately this number was less than 1, the 5/6, we end up verifying the second moment. OK. So that ends the proof for the triangle lattice. But let me mention, though, how much room did you have to spare? Not so much. I had 1/6 here. If had that been a 1, it wouldn't have been integrable. I needed something less than 1 here. I had 1/6 room to spare. Corollary, the Hausdorff dimension of the set of exceptional times is 1/6. Okay. Of course, you don't know these facts if you haven't seen these things that you'll see in the elementary course on Monday, but the Hausdorff dimension lower bounds are usually given by, when you do second moment methods, how much room did you have to spare? I had 1/6 amount to spare in the exponent, and that usually will tell you a lower bound on the Hausdorff dimension of a sixth. I can mention here, I don't think I'll have time to do it. using some of the exponents you saw in the other course, one can show an upper bound on the Hausdorff dimension is 31/36. Okay, so this method, what did this method do? It worked for the triangle lattice. It gave a lower bound of 1/6 on the Hausdorff dimension, which is quite far away from the upper bound. And the method wasn't able to be worked for Z2. We didn't have the critical exponents, and then we can't do the Z2 case. So I want to sort of speed up a little to get to the geometric thing. Maybe I say, well, it's described in the notes, so maybe, in fact, I won't do it, but I'll just tell you, what the algorithm is, and then it's described in the notes how it works. So what I want to do is I want to know, is there a path from here to here? So what I can do is I can send a radial interface from the outside to the inside. So this is a path which has white on the right and red on the left. And I keep going and see if I hit this or not. Now, what's going to happen with this one, it's going to make loops. Makes maybe some loops this way and some loops the other way. Now, the loops, one loop's good, one loop's bad. I want to know if there's a white there. If the loop goes like this, if my loop comes around and connects up, then I've got a red circuit separating me, and I don't have a path from here to here. On the other hand, if it goes around the other way, that just corresponds to a white loop. That's OK. I continue sort of the radial interface inside. And this original point was chosen uniformly and using very similar things that we did for the revealment of the crossing events. You end up getting, you could draw a picture and sort of convince yourself that the revealment is more or less this. More or less, if you imagine, maybe a good picture is here's a little r, here's a giant R, and if we take something about U about here, what has to happen for U to be revealed? Well, if this is, say, that's distance U, that's distance 2U, there's two things that have to happen. There has to be a path from here to here. That corresponds to a one-arm thing. And sort of in here, the interface has to come in, and that corresponds to a two-arm thing. And you compute things, and you end up getting that as an upper bound. I think it's described in the notes, so I don't want to do that because of lack of time. OK. So that's what the randomized algorithm approach gives. Now let's move over to the geometric approach. And the key thing is a lot of this is done some of this is done the same, but what do we need to do in the end is this gives a 1 over t to the 5/6 exponent. We want to lower this number 5/6 to a much smaller number. And ideally, if one would believe this is the Hausdorff dimension, we would want to bring this down all the way to 5/36. And the hope is that the geometric approach can do that. OK. So now we want to move to the geometric approach. And we want to do two things. One is to try to explain why the Hausdorff dimension is bigger than or equal to 31/36. And hence, by this fact here, which I don't think I'll be able to argue, but which is not so hard to prove. By the way you prove this is what you do is you take the argument I did in high dimensions, and you just do that argument as well as you can. You won't end up getting that the mean is finite. You'll get the mean is something else, but that's actually a very good exercise. learn Hausdorff dimension if you don't know it. Prove this upper bound by taking the argument we did in high D and try to generalize that argument. Anyway, once the geometric argument gives this as a lower bound, that calculates the lower bound. So that's one thing. And the other thing is that Z2 has exceptional times. So I'm hoping to sort of give you a flavor, more or less arguments of these things based on some properties of the spectral sample. Okay, so if we stick to 1 to begin with, so spectral behavior, I'll call it. So in this argument, we're not going to break up the thing into two different scales, little r and big R. We don't want to do that. So behavior. So I'm going to consider the spectral sample for the event for the event that there's a path. Okay, I call this F sub r. F sub r is the event that there's a path from the origin to r away, and I want to understand its spectral behavior. So I'll just call this script SR, and the spectral behavior is the following. If you look at supposed to be an S of R, is at most alpha 4 of R squared. This is at most O of 1 alpha of R squared over alpha of little r. Alpha sub 1 is always alpha. Sometimes I'll just write alpha. So the probability that it's below here is given by this thing here. Okay? And Q is what we called the spectral measure. So if we sum up all the Fourier coefficients up to this level, we get this. Notice, if you compare this to what Christophe did yesterday, he had for the crossing probabilities, he had an upper bound on something like this. But the thing involved the alpha 4 terms. It involved the 4 exponents. They don't appear here. You get something different, and I'm hoping at the end to explain why you don't get an alpha 4 here. You just get things like this. Okay, so I want to rewrite this. For the triangular lattice, this thing is r to the 3/4. For simplicity, let's just assume it's exactly r to the 3/4. Then consider sort of the mapping. I'll call this, I just want to consider the inverse of this. So r to SR is the inverse of r goes to r to the 3/4. So this is just S of r is r to the 4/3. Basically, I just want to rewrite this where I can put a k here, and put something here in there. It'll be slightly easier. So if I rewrite this here, probability it's less than k. This is at most O of 1, alpha of r squared. And here I have alpha 1 of S of r, which is the same as alpha 1 of r to the 4/3. Okay. So this is, once we have this control on the spectrum, we can look at the correlations between f of omega and f of omega t. So this is exactly the term that came up in the integrand in the integrand before. So, well, I always can subtract off the mean. Okay, I won't. So this is the sum over all s. Sum over all s of e to the minus t times s times f hat of s squared. This is exactly the way, this is, again, for the exact reasons before, this is a noise version of that, with epsilon being 1 minus e to the minus t. So you can represent the correlation in terms of the Fourier picture, and you get exactly that. And now what I want to do is I want to break this up depending on where the spectrum, the size of the spectrum. And so I'm going to end up breaking this up in terms of, I'm going to look at all the s's whose size is between k minus 1 over t and k over t of e to the minus t s f hat of s squared. So I'm just breaking up the s's depending upon the size. So what happens now, if s is sitting around here with the divided by t, this exponential becomes more or less e to the minus k. So this is about some e to the minus k, and then I have, and then what I'm left with when I sum up all the coefficients in this regime, this is going to be at most the amount of mass that is sitting below k of t. So this is at most the spectrum sitting below k of t. And now we just stick in what we get up there. So this thing here is I sum over k. I have e to the minus k. This thing, first of all, I'll bring out an alpha of the r squared. That's this term. And then I'm left with e to the minus k. E to the minus k. And then the amount of spectrum below k over t by this thing is I have 1 over alpha 1 of, I have to put in r to the 4/3, so I end up taking k over t to the 4/3. And then if I use what the one-arm exponent is, this sum here becomes sum over k, e to the minus k, k over t to the 4/3, 5/48. So what's happening here is we have our second moment here, our mean squared here. I look at this thing here. I can pull out the power of t. This whole thing is at most 1 over O of 1 times 1 over t to this power. And what is that power? It's 1 over t to the 5/36 power. And the sum over k is e to the minus k times k to some power, and which is an O of 1 term. So I end up getting the correlation is 1 over t to the 5/36. And this is exactly what one needed to get the Hausdorff dimension. So I don't want to do too much more. I'm sure people are slightly tired after intensive 2 weeks. So I think what I'll do abbreviated versions of a couple things. So I'll turn one of the things I was going to do into an exercise. So I'll state I'll tell you the key fact. So the proposition is for Z2, there exist exceptional times. Proof. Try to follow proof that Hausdorff dimension is bigger than 31 over 36 using the spectral bound. And this is a doable exercise. I mean, putting everything together, with this spectral bound here, together, so using the spectral bound plus something that Vincent had done, which is the following thing. Proving an inequality like this. First, let me tell you something about this inequality. Let me say, if this were not there, this is an inequality you saw, perhaps in Hugo's exercise sessions. Okay? So what happens is the probability of having a 5-arm exponent is exactly 1 over r squared. That's the probability of having a 5-arm exponent. By the Vandenberg-Keston theorem, you could say that, okay, the probability of having a 5-arm exponent means you have to have a 4-arm exponent and a separate 1-arm exponent. That gives you both of these. So if I didn't have this, the estimate for the 5-arm exponent plus Vandenberg-Keston would give you this inequality. But what Vincent showed was that you can do this with you can improve the exponent. This is bigger than or equal to r to the epsilon naught. And this positive epsilon naught is necessary to make the argument work in the Z2 case. Okay, so I leave that to you. Finally, let me say just 2 words about this spectrum, and in particular, this upper bound, is it right here? Right, that does not have a 4-arm exponent in it. So as Christophe described, when he looked at the crossing event, he showed you that probably that the spectrum, say non-empty, is at most r squared alpha 4 of r. He said he argued this becomes r over r squared alpha 4 of r big R squared. Because the argument was you break this, once to get the spectrum down to that size, I should break this up into mesoscopic boxes of size little r by r, and the hope is that all the spectrum should be concentrated in one of those. And the probability that you have spectrum only in here corresponds to this term, and then the number of such squares in this box correspond to this. So you get an alpha 4 term. Now, what happens if you look at this event instead, you can again sort of break things up into r by r boxes. But it turns out that unlike here, where the spectrum sort of could sit in any of these R boxes, for the radial event, the spectrum is going to tend to sit much more here than further out. This is not so unreasonable if you think of spectrum as sort of like being pivotal. Clearly, the origin has a much higher probability of being pivotal for this event than this little person out there. So it's clear that the center of the box is sort of maybe going to play an active role. So I just want to do an extremely quick computation to show you that probably the spectrum sits in this box. Centered there has that upper bound. And then if you were to believe that this is the main contribution compared to the others, because the radial event has to come from here, then we'll get that upper bound. So maybe I call this box B. So if we look at the probability that the spectrum is sitting inside of this box B. Remember in my last lecture, we expressed this probability as simply the L2 norm of the conditional probability of the event FR given what happens in this box squared. Okay. Now this is easy to get an upper bound on. So I want to know what's the expected value of having a path from the origin to distance r when I condition on the box B. Well, if when you look at B, there's no path from here to distance r away, then you know that the event can't occur. So the only way FR can occur is if there's a path from here out to here. So that gives you a contribution of alpha 1 of R. And then if that happens to occur, that's information here, then the probability you can get from the little r to the big R box, that's going to be the annulus event, and that gets squared. So that becomes alpha big 1 r to big R squared. And that's exactly the upper bound I have if you just use now you use quasi-multiplicativity, and you get exactly that upper bound. So the upper bound is justified if this is where all the mass is, and then you have to, argue. It's very involved that you have to argue with the spectrum and show this is sort of where it sits. Okay, so that I think I'll end there for the dynamical percolation, and thank everyone for coming here on Saturday. So, thanks. Any questions?